course, 24. And so those of you who didn't vote, you deserve a serious something. But I'll leave that for someone else. Combinations. Combinations we use when order doesn't matter. That doesn't mean that you'll never use permutations when order doesn't matter, because sometimes it's convenient to pretend briefly that it does in a probability problem. But in general, if I have n distinct objects, n objects I can distinguish from one another, and I want to select r of them to put in a set, then the number of ways of doing that is n choose r. If I don't care how, what order they came in. So for example, the number of possible poker hands is 52 choose 5. If I got a royal flush, I don't really care whether you gave me the ace first or the jack first. I'm just so pleased I have a royal flush. Not that I've ever had a royal flush or ever even won at a card game. And there's no bitterness in my voice here. The fact that I have 2 graduate students who supported themselves almost entirely by beating people at cards and wanted desperately a large share of my income as well. That I'm also not bitter about that. N choose r is n to r factors divided by r factorial. Or the definition you've seen most is n factorial over r factorial times n minus r factorial. Lotto 649 is a perfect example of this, because it gives out prizes, albeit rather small, depending on how many numbers you chose which match the 6 numbers that were drawn. There are a total of 49 numbers in a giant urn or ball someplace. 6 of them drop out. You have previously picked your 6 numbers. There's actually a picture of a ticket here, I think. There are the numbers on this ticket: 32, 03, 04, 05, 08, and 13. And so if you have 5 numbers that match their 6, 5 of their 6, then you get a prize. And if you have 4, you get a smaller prize. And if you get 6, you get typically a very large prize. How large would that prize be, say? Well, depends what's in the bucket. They do make enough money to put it in a bucket. By the way, I put a link to the Ontario Lottery Corporation's table of payoffs for various games in 649. Don't forget, of course, that they take a large chunk off the top. And moreover, if you win and somebody on the other side of the province happens to choose the same number, then you have to share the prize with them. And I hate when that happens, but it's better than no prize at all, I guess. So the question I'm asking here is not so much the probability that you win, but the probability, say, that no odd number is drawn. In fact, they perform all sorts of tests on the lottery numbers in order to see whether or not they are random or whether they're drifting away from random over time. The sample space in this case consists of all combinations of 6 numbers. The order in which they come out doesn't matter. So there are a total of 49 numbers, of which 6 fall out of this giant spinning ball. The probability that a particular combination of 6 numbers falls out is therefore 1 over that. 1 over 49 choose 6, and 49 choose 6 is big. It's about 13.9 million. When you buy a ticket, the probability that your ticket wins is approximately 1 in 13.9 million. The question, however, was the probability that no odd number is drawn. So how do we determine that? Let me see, I think I have another. There are 25 odd numbers in total and 24 even. So in fact, there aren't equal numbers of the 2. In order that I draw even numbers, I have 24 choose 6 ways of doing that. 24 choose 6 choices in which all the numbers are even. The probability of no odd number, therefore, is the probability they're all even, which is 24 choose 6 divided by 49 choose 6. I figured that out. It's somewhere around 1%, but that's beside the point. So if you're buying a lottery ticket, let's suppose you must buy a lottery ticket. It's better than the horse race you went to last class. The payoffs are maybe small, but there is always that chance of the huge prize. What is a winning strategy? Well, the first winning strategy is don't buy the ticket at all. No, actually, the first winning strategy is buy the corporation and run your own lottery, because then you get to take 60% of everybody else's money. That's a lot more fun. But failing that, your winning strategy is to pick a number no one else would pick. I've seen books. You can buy a book. In fact, if you want, I'll sell you a book. Come on, I mean, I've got them up in my office. Well, I don't at this moment, but if you give me 5 minutes after class, I can make you a book of winning, potentially winning lottery corporation numbers. Why is it better to pick it from a book? Well, just because you're less likely to choose the very numbers that somebody else does. Why is that a winning strategy? Well, it's actually not a winning strategy. It's a losing less strategy. Because then your chances of winning is 1 in 13.9 million, but now you may not have to share it with 10 other people, all of whom are, or 20 other people, all of whom are in love with the numbers 7 and 3. 3, 7, 17, 23, and so on. So basically, the only strategy you have is to try and pick numbers that are unusual, at least in other people's world, so that you don't have to share the prize with too many people. You will, of course, have to give money back to your mother. Here is a question which I think is also at the end of the chapter. We form a 4-digit number by randomly selecting and arranging 4 digits from the numbers 1 up to 7. We are selecting without replacement, so I can't use the same number twice. Find the probability that the number formed is an even number over 3,000. All right, but you'll find on the practice quiz, in fact, you'll have questions something like this that take a little bit of thought, really, in enumerating the possibilities. And in this case, you really need to go through it in 2 steps. You need to first look at what the last digit can be. Let's pretend, again, is an important feature of this problem. Let's pretend you fill in the last digit first. There's no harm in doing that. Let's suppose that the last digit is 2. Now, what choices do I have for the first digit? It has to be a number bigger than 3, 3 or larger. So the first digit could be any one of 3, 4, 5, 6, or 7. There are 5 choices for the first digit, and having used one of those, for example, having picked 3, I now have 5 choices for the second digit. I've consumed 2 of my 7 digits. I have 5 left to select among. Similarly, when I move on to the third digit, now I've used up 3 digits. I have 4 digits left. So that's that choice. That's this part. This is 5 times 5 is 25 times 4. That works out to 100. But there's another possibility. The last digit is either a 4 or a 6, and I have to treat that differently. Get used to it. Sometimes you have to break problems into half. If you're lucky, each half is not that complex. If I pick the last digit as a 4 or a 6, well, I have 2 choices for the last digit, 4 or a 6. But what have I got left now for the first digit? It has to be a number 3 or greater. So it's 3, suppose this turned out to be a 4. 3, 5, 6, or 7. I only have 4 choices for it. That's why it's different than the first case. I have 4 choices for the first digit. Now, having used up those 2, I still have 5 for the second and 4 for the third. So I'll add up those 2 different possibilities. Why? Because of the use of the word or. I should have put it in here. I did put it in here, but it's not big enough. or. Because I used the word or between these two choices, I added the number of combinations, the number of possibilities in the first case to the numbers of possibilities in the second case, and divided by the total number of ways of filling up those 4 spaces with 7 digits without replacement, which is 7 times 4. And of course, it's just as easy, it's probably easier to solve this problem just filling in the first and last digit that way as well. All right.